Today I'm going to talk about LLM watermarking using mixtures, and as a joint work with Ramon Verschining. I would like also to special thank Professor Pierre Baldi in UC Irvine for suggesting us to work on this topic. So let's start with some basic motivations for watermarking. Perhaps the most standard motivation for this problem is, well, problems with deepfakes and misuse of ChatGPT, and huge concern with AI generated text. So text generated by AI causes a big concern, you can see in this news. So our goal is to study a preeminent technique called watermarking to try to address this issue. So our goal here is quite simple. We want to identify text generated by watermarking and large language models. The problem, of course, that LLMs are getting better and better and imitating the human writing. So I don't think that we are in exactly this position now, but it's getting harder and harder. So you want a proper way to identify it, not relying on our eyes. And so watermarking is one way to phrase it. We want to embed a signal in the process generation of the text that does not alter the quality of the text. Well, we still want this text to be, output to be useful and as useful as the LLM is. But we want this text to be detected as watermarked once this text was generated by the LLM. Once we have an additional piece of information that we should call the key. So we embed a signal, and this key somehow correlates with the signal that we should be visible on the text. And just a kind of remark, because I started introducing the main application of watermarking concerned about deepfakes and misuse of ChatGPT. There are plenty of other applications that I'm not going to focus a lot. Another aspect also of the talk is that I put the abstract, I think, about mixtures and computational gaps. I will skip the computational gaps parts today because it's more theoretical and time constrained. Okay, so don't. It's not going to be a coincidence that I'm not going to talk about the second part of the abstract. Okay, so let's focus first on the basic requirements of watermarking. So we first want to be statistical undetectable. So any algorithm basically solely on the text, you cannot see the watermarking. So it should not be visible in your text directly. So we want some property called completeness. It's possible to detect the watermarking with an extra piece of information, the key, right? Once we inject the signal and the text comes from the LLM, you should use the key to detect this. There is a kind of hypothesis test in the background that you're going to see in soon. And soundness, of course, we don't want false positives in terms of statistical language, right? We don't want to pick any text and accuse it of being watermarked, especially due to delicate applications. So if the text was generated completely independent way from our key or watermarking scheme, then we should not detect this as watermarking. Okay? It's clear? Okay. So let's set up a common ground, probably for the audience today, this is a bit redundant, but just to make sure. We are going to use very little about the LLM machinery math. So we just want a procedure. We just need LLM to be like a procedure that computes the probability distribution P over D tokens. Okay, so, and this is what more important is that this autoregressive way, you sample the first token, the LLM computes another probability distribution, samples the second token, that the probability, and computes another probability distribution. And this second probability distribution, it depends directly on the last one, right? And the process is repeated until you finish the text. So just what we need basically from the LLM, you can view it as in probability as kind of discrete process. But the key difficulty in these problems is that, well, for a probability perspective, trained in probability statistics, the tokens are not independent and not identically distributed. So this already rules out a lot of tentatives that you can try. Okay, so a mathematical framework that we're going to adopt today, we are going to identify the vocabulary, so the set of D tokens with the set 1 to D. So I'm going to talk about token 1, token 2, token 3, and so forth, not token any like part of English or whatever, any language. So it's going to be token 1, token 2, until token D. Of course, it's not the things that they're going to do, they do not depend on the assignment, properly speaking, right? It's going to be invariant. So let's establish that watermarking is going to have two phases. The phase 1, a sampling algorithm, then at each step that you're going to sample a token, our watermarking algorithm is going to pick the probability P computed by the LLM, and going to compute a watermark distribution Q that's supposed to satisfy the previous requirements, right? And the detection algorithm, that's the hypothesis testing that I was talking about, the algorithm, you need to have the text and have the key and solve this hypothesis testing. So if the text was independent from the watermarking, that's what we call human-generated. And the alternate hypothesis is that, well, the text comes from my watermarking distribution. Okay. So let's see some examples. Like in the literature, there are tons of proposed methods. That's like impossible to review. Like you can spend the entire day. There are thousands of methods. But I try to briefly summarize in two categories. So this was going to be the first pillar of watermarking schemes. What I mean by that is that a lot of watermarking schemes were based on this idea. So tweaking this idea or pushing forward this idea. So this idea by Kirchner, Gapin, Wendt, Katz, Myers, and Goldstein, they partitioned the tokens into red and green lists. Quite intuitive, right? You have the key, that's only you know that which tokens were colored as red and which tokens were colored as green. And then intuitively, you increase the probabilities on the green list while you decrease the probability in the red list. Usually, in the classical way, they do this in the softmax formulation before taking the softmax function to guarantee this is a probability distribution. So here, it's already we have a kind of hyperparameter in the back. How much do you perturb? And this hyperparameter, well, I'm going to mention more about this later, but hyperparameters, they cause problems because you don't know the probabilities, right, that what's going to be. But okay, it's intuitive that you make the tokens in the green list more likely, and in the red list you decrease it, so you should see in a watermark text a lot of green tokens. So the detection algorithm just counts the number of green tokens. And somehow has a rule that tests statistics that say, well, if there are too many green tokens, this is not coincidence. This comes from the watermark text. So basically, this line of work, they have this line of work in watermarking based on this idea. They have the great feature that's sorry. Can you see here? Okay, this green is implementation, so they are very easy to implement. Just color, pump the probabilities, and you count the number of green tokens, so it's kind of linear test statistics. And easy interpretation, say. But they alter the quality of the text a lot, because at each time you bias toward the green tokens, and if your text was supposed to use the red tokens, it start biasing, so on. What, sorry? Yes?
But here, in order to watermark, like you have to be one generating the text, right? Like you have to, like, OpenAI has to agree to do this, basically.
Yeah, you have to. Yeah, it's this watermarking that I'm going to talk today is that you inject the signal on the LLM procedure before the prompt. But yeah, it's part of the LLM, and then you just look the text output. Okay. It's a good question, yes. Another question in the field that I did not see much work about is can you do this from the text alone?
There's these apps that like lead to the GPT-0.
Yeah, directly from the text.
Yeah, like you paste the text and it tells you how likely it is to be generated.
Okay, to detect, but not to implement the watermarking. Right. I see. So it's another technique. I see. Yeah. I see. Interesting. Yeah, thanks for letting me know this. Yeah, I'm focused on the watermarking technique. I'm not going to rely on cryptography tools as well. Yes?
Yeah, so for this type of techniques, I believe it's detectable without the keys, right? Because if you look at the tokens from one sample, you'll see that their distribution is scaled from the regular text distribution. Like the tokens will concentrate on a support of the vocabulary, right?
Yeah, but how can you run just from the text alone this kind of test without knowing the key? Well, we don't know which red and which is green.
But you can compare with if you take all the natural language and you can compute their distribution of the tokens. Would that be a concern to you or no?
No, that's not my method. But yeah, I don't think that's like you can do this accurately and like one of the problems that there's a lot of false positives in this kind of techniques. So, but we could see. Okay. And also, well, not this requirement. The requirements violated here, like it's supposed to preserve the probability distribution, the watermark. So you're not supposed to detect watermark or not from the text alone. That's why the piece. Yeah, here because they alter the quality of the text. Yeah, exactly. They violate this the first.
Yeah, exactly. Okay.
Yeah. Okay.
Thanks.
Good. Okay, so part 2 is roughly this idea that you sample uniform random variable when you're going to generate the token, a uniform random variable 0, 1, that's going to be your key, and split the interval 0, 1 into D pieces, D being the vocabulary size, and then each length of your division has the length proportional exactly the probability that you. So if you have like 3 tokens, say P1, P2, P3, you split the interval P1, P2, P3, and you can check the probability is the same. It's actually widely used technique to generate discrete categorical distributions if you can generate a uniform distribution. So the idea that in the watermark text, the text correlates with the corresponding uniform random variables used to generate it. So this was a very influential idea. So here the quality is preserved, the distribution is the same, but the very complicated detection schemes. So we lose the test statistics that was like just count the number of green tokens that has a lot of properties, linear, and etc., easy to interpret, to more complicated detections. So usually detections relies on these ideas. They are more convoluted, especially computationally. So what we are going to try to do is to interpolate between the two worlds. Yes? Yeah, suppose that you have 3 tokens, say, and you split your interval 0, 1 into 3 pieces, and each piece that has length like equal to P1, equal to P2, equal to P3. And so if the random variable falls on within the first part, then you sample P1, the first token, and so on. And what's the probability of the random variable to fall in the first piece is exactly the length, because you make it uniform between 0 and 1. Okay. So what we are going to try to aim here is to do some kind of interpolate between these two. We want elementary method, but not biasing the quality of the text, okay? So our theorem it's simplified as follows. We have a watermarking scheme that is statistically undetectable, and after giving any delta between 0 and 1, if the text, the length of a text is sufficiently large, then you're not going to have false positives, you're not going to misaccuse any test with probability 1 minus delta. And also, we have the following condition. So suppose Pj star is the most likely token in each step. So P1 star is the probability of the most likely token in the first step. P2 star is the most likely token in the second step, and so on. So at each time, the LLM computes a probability distribution, right? So there will be a token that's the most likely one. So if we average this here, 1 minus the most likely token at the time j, or suppose there is a typo here, suppose the sum j1 to n, 1 minus pj star. If this beats this deviation term 2 log 1 over delta divided square, that's order of square root of n, this beats a bit by a constant delta, gamma, then with high probability we detect that text was watermarked. Of course, the high probability depends on gamma, right? So how natural this condition is? Well, if at each time the probability distribution is too spiky in the sense that the next token is almost a deterministic function, so it has very low entropy, then we should not be able to do watermarking, right? So this is kind of that appears in all the works, but here our concept of entropy is hidden in 1 minus the most likely token. And this is very easy to interpret. It's not a complicated function. And we should think this as, if you want some asymptotics, is going to 0 with like square root of n. So this quantity on the left-hand side just need to be bounded away from 0. Okay. So let's see how we construct this watermarking. I will start with basic baby example mixtures. I don't know, I always think in the simplest version in Gaussian to see if to explain things, maybe. So suppose, of course, I just said it's not IID, but let's make the exercise that's IID Gaussians between 0, 1, what you want to watermark. Well, we could generate signs, R1 to Rn, and generate the Gaussian by sampling from a folded normal distribution if the sign is equal to 1, and minus the folded normal distribution if the sign is minus 1. So you mixture two Gaussians, two folded normals, right? One positive and one negative. This exactly gives a Gaussian. So by just observing samples of Gaussian, you cannot tell it. So you cannot be able to tell if it's watermark or not, but a watermarking test is pretty simple. We just count the number of negative components. How many samples went negative? Because of our generation scheme, our key is the sign, so if you multiply by the sign, you're going to take the absolute value. And if the Gaussian was completely independent from my sign, multiplying the sign is going to have the same distribution. So let's try to explain baby steps of a proposed algorithm. Let's suppose that we have 6 tokens. Of course, we don't, but this is for the sake of simplicity. And remember that I identified the tokens from 1 to D, so I'm going to talk about token 1, token 2, token 3, token 4, token 5, token 6. And we have these probabilities, so the probability of the first token to be chosen is 0.25, 0.20, 0.10, and so on. We start by assigning groups. That's basically a partition. Group 1 and group 2, so half of them are group 1, half of 2 are group 2. If they're like an odd number of tokens, it's usually the LLMs that I found. There are no odd tokens. It's very easy to fix this issue, okay? You can just remove you can do some tricks. So suppose for now that we have even number of tokens. So we do a group assignment, a partition, and then we rank. So we first looked group 1, and we ranked from the most likely token to the least likely token. So we have here, it's not working, okay. We have here 0.25, is group 1. You have here 0.10, is the group 1. And you have here 0.05, group 1. So you rank this as first, you rank this second, and you rank this as third. You are ranking just among group 1. So you save this rank, and you do the same thing for the group 2. So the most likely token group 2 is 0.35. So we do this ranking. Okay. And then we compute a perturbation, epsilon, taking the minimum among the following. The first row, you have P1. So we take the minimum of P1. P1 is group 1 and was ranked as first. Which other token is ranked as first as well? The fourth token. The fourth token is ranking first. So we compare the minimum between P1 and P4. This gives 0.25. We go second row. We take a minimum of P2. And P2 has rank second. So the third token also has rank second. So we take minimum between P2 and P3. That's 0.10. And we continue like this. We don't need to compute the third row because we already used P3. So 0.10. Fourth row already appear to compare P1 and P4. And P5, P6, they are equal. Okay? So these are going to be our keep epsilon this as perturbation. So we kind of do a mixture. If R equal to 1, we increase everyone in the group 1. And the amount that we increase it's not homogeneous anymore as was before. We bump the first token here, group 1, we bump by 0.25, while in the fourth token, we decrease by 0.25. That's why we take the minimum. Because if we bump this guy by 0.35, it's going to be too much. It may be too much, right? Here we will not pass 1, but it could be the case that I go above 1, then this is not a valid probability distribution. And when r is equal to -1, then we repeat the process, but we flip signs. So we decrease 0.25, and here you can see the fourth row increase 0.25. So in this way, I preserve the probability distribution of the token to be the token 1 to appear. I created a bias when r equal to 1 to the group 1, and I create a bias when r equal to -1 to group 2. So which properties that our watermarking scheme has? So the probability distribution Q, the watermark, behave as a mixture of two distributions, one for r equal to 1, other for r -1. That's why I introduced the baby example of mixtures. So due to the symmetry of R, probability half is 1, probability half -1, it's a fair coin, we have undetectability. And also, our key will be the group assignments. Let's say 1 if it belongs to group 1, and -1 if it belongs to group 2, and the sign R. So the idea is that if the token is watermarked, then R times delta evaluated at X. So I'm identifying the tokens from 1 to D. So I'm looking the indices of delta corresponding to the token. R times delta of X is more likely to be positive. In particular, you can show that this expression holds. So you can see mathematically, you can show that the expression, this expected value, is proportional to the sum of all perturbations. Okay? That's epsilon of 1, epsilon 6. That will be the column before. So this, like this column here. We sum this column. And this sign just means that's like proportional to. Like it's, actually you only need that's at least this quantity by a constant. And the constants here you can compute. I'm just hiding for simplicity, but you can compute all the constants. So otherwise, well, if the text was not watermarked, so the token's completely independent from my key delta, the sign is independent of X, so expected value of R is 0, so it's going to 0 everything. So we have like already a test region to arising here. When it's watermarked, it should be bounded away from 0, this quantity, and when it's not watermarked, it should be 0, or very close to 0. Okay, so the question is how large this perturbation can be, right? Fortunately, it's reasonably simple to estimate. So intuitively, we would like to assign the group 1 to have the most likely token, the group 2 to have the second most likely token, because we're going to take minimum between two probabilities, and we want to maximize this quantity, because the bias that I got when the text watermark is proportional to this perturbation. So I want to do a most aggressive perturbation that I can, right? And if I could do this assignment, assign the most likely token to one group, the second most likely token to other group, the third most likely token to one group, and the fourth to other group, then I would maximize the bias that I can get. It's the best that I can hope for. So you can show that in this case, if you do this, at least the P star is the probability distribution rearranged, so this is at least the second most likely token, the probability of the second most likely token, the fourth most likely token, and the last most likely token would be the least likely token. So this you can easily show because that's at least 1 minus the most likely token. This is how 1 minus the most likely token appear. Here, because like P star 2 is at least P star 3 plus P star 4 divided by 2, right? The second most likely token beats the average of itself plus the next. So doing this, you can show that this quantity has at least 1 minus P star of 1. Well, the problem that I said this is Oracle assignment because I need to know the probability distributions before doing this assignment, right? And I was supposed to generate the key before, regardless of what the prompt is. The text we're going to be generated. Fortunately, we have a combinatorial tool and small combinatorial lemma that says that if you do a partition at random, then this is the case. Here, where we lose constant, the 1 of 20 in our main theorem comes from this fact. We can improve this constant. If you care about the 1 of 20 is not a super small constant. We can improve this constant at the price of a more complicated expression based on combinatorial way. But we opt for the simplest possible formulation. So to generate the watermarking scheme, preserving this undetectability for the whole generating process, we generate independent keys. So Rj and delta j are copies of R and delta. And we run the detection algorithms, like given the text, we compute this test statistics. We average Rj, delta j, xj. If you take the expected value, or expectation is linear, this average is supposed to be bounded away from 0 when we have watermarking. When the text is not generated by our watermark distribution, remember that the expectation was 0, so this is going to be very close to 0. This we expect, well, we have some bounded random average of bounded random variables. If you believe that these things roughly concentrate around its mean, so we have a test, right? We just recalling that in the one watermark, the expectation is 0. So z is close to the expectation. The expectation is 0, so z should roughly be close to 0. And in the watermark text, the expected value of z is bounded away from 0, proportional to 1 minus the most likely token. And z should be close to expectation. So expect that in the watermark text, the z to be bounded away from 0. And we have a test statistics that just tests if z is larger than this square root of 2 log 1 over delta divided by n. That's why I need that condition that says that the average of 1 minus the most likely token over each step should beat this deviation by some constant. The interesting aspect here, maybe in a statistical viewpoint, is that this does not require any extra knowledge. It's not sensitive to very delicate hyperparameters like entropy of the text distribution or this kind of things. Because these hyperparameters, they cause a lot of harm. Because when you see the text, sometimes it's hard to grasp exactly what's this entropy R. So we just need z to beat deviation terms in which I can control the confidence level, I know the length, and so on. This is highly desirable, right? Especially because of some kind of stability thing, right? You don't want to draw different conclusions if you set up different hyperparameters. Okay, so to wrap up some implementation, I asked to write a story about Craters and ancient Greeks, And I put a more specific prompt to see if the watermark or the watermark, they start talking about completely different things. Fortunately, it was not the case, right? Because here, the first sentence was even the same, and then here, the unwatermarked, they talk about fueling the destiny and village, and below was some kind of farm and chosen by God and etc. So this is storytelling. At least they are reasoning about similar things. Okay, so that's all that I wanted to talk today about our method. Some future directions, sharper lower bound. Well, mathematicians always ask, is this the right quantity? Sum of 1 minus the most likely token, tap J. It's a good quantity because it's easily bounded away from 0. But we have sharper lower bound. This is the right quantity. This is necessary. Is it necessary in some sense? Because the probability is exactly 1, then you cannot watermark anything. But exactly this shape, we don't know. We can improve our scheme on the extra assumptions. For example, if you assume that reasonable assumption that the distribution concentrates in very few tokens, like most of the distribution, like 80% of the mass is concentrated around 3 or 4 tokens, you can improve, make things faster. Also, if you assume that if you create a partition since the beginning on your vocabulary, and you are not very unlucky that at most of tokens, the mass will be concentrated in one group rather than the other. This is where our method fails, right? When all the mass is concentrated in one group. That's why you need to take the groups at random, etc. But we just assume most of the time we are not that unlucky. Then we can remove this delta as the key, and then we get the key just random signs. That would be like 1 bit per token. Pretty reasonable. And a future direction to, well, there is the issue of robustness. If someone start editing your text, how things are going to work, right? If you remove some tokens, add some tokens. The problem with this, there is a very interesting trade-off that has been reported in the literature, the conflict between detectability and robustness. Because if you start editing and adding, then if you do like this kind of independent key, then this key will misalignment. But on the other hand, if you don't do this independent key, once you condition from the past, this is no longer independent, so your key is going to affect a bit the quality of the text. So you could see somehow 2 extremes of this example. The first one, that ring and grad list, it's more robust, but suffers from the quality, and the other preserves the quality, but suffers about robustness. Okay, that's what I have today. Thank you very much about your attention.